Number 63, we have a 1.2 kilovolt power source, a 6.5 microfarad capacitor, and three resistors that are all 0.73 mega ohms. With C completely discharged, switch S is suddenly closed at t equals 0. At t equals 0, what are the currents and in resistors 1, 2, and 3? All right, so the critical part here is at t equals 0. Remember, an uncharged capacitor acts for all practical purposes like a wire. So it's just acting like a wire here, which means these two resistors are now in parallel with each other. Meaning the total resistance of these two is just 0.365 mega ohms. That is in series with the other resistor up here. So the total resistance, just the sum of those, is about that's supposed to be a comma right here, 1,095,000 ohms. Our voltage, again, 1.2 kilovolts. And so our current then, which is all flowing through this top resistor, is going to be just the battery voltage divided by the total resistance of the circuit, which is given by this. Now, when the current gets over to this point right here, it's going to split. Part of it's going to go this way, and part of it's going to go this way. So the current through R2 and R3 isn't going to be the same value. But here's the good news. Because of symmetry, if you look at, we have equal resistances on both sides. Again, the capacitor's acting like a wire. The current's going to split up equally. And so it's going to be half of that, 0.550 milliamps for I2, and the same thing for I3. Now we get to the next part. As t approaches infinity, what's going to happen to all these as well? Well, now we actually have to do a little bit of work. Let me clean this off here real quick just to avoid confusion. Remember that as t approaches 0, or approaches infinity, the capacitor will be fully charged and there will be no additional current flowing down through here. In fact, it acts like an open circuit, meaning that this whole part of the circuit basically disappears. What's the current going to be now? Well, the total resistance, just the sum of these two, or 1,460,000 ohms, again that should be a comma, and if you divide that by the voltage, we get the current through I1, or R1, is going to simply be 0.822 milliamps. That exact same current is going to be flowing through this resistor down here. But because the capacitor is completely charged, there is absolutely no current going through this last one, and so the current for R3 is just 0. Now, next questions. What's the potential difference across resistor 2 at t equals 0? Well, at t equals 0, we know the current was 0.550 milliamps. The resistance was that. If you work it out, there's a 400 volt difference. As t approaches infinity, the current we now know drops to this, which is about, or actually rises to this, which is going to give us a voltage drop of 600 volts. Finally, sketch V2 versus time between these two extreme times. So here's our graph, and I'm going to put 400 right here, and 600 up here. And what's going to happen? Well, we know that our graph is going to start out at 400, and it's going to approach 600 asymptotically as time approaches infinity. So it's going to start out here at t equals 0, and then slowly approach this value asymptotically. And it's not a linear graph, it is a nice exponential one. Hopefully that makes sense. All right, good luck.